The electricity that we generate in power stations has a very high current. If we passed that high current onto the national grid, into the wires and cables to transmit it all over the country, a lot of energy would be lost as heat. And that's not very good. We don't want to lose energy that we've spent all these resources generating. We don't want to just lose it to heat as it's being transported around. So we want to lower the current of that electricity before we send it around. We don't want to lose any power though, and since power equals current times potential difference, that means if we want to lower the current, we need to increase the potential difference. So how can we change these things? Well, the answer is we use something called a transformer. A transformer has three main components. It has two coils, a primary coil and a secondary coil, wrapped around an iron core. Now the iron core may be laminated to stop any current flowing through it. We don't want the iron core to conduct electricity. And let's explain how it works. Okay, well, we start off by putting an alternating current into the primary coil. So we have an alternating current flowing through this primary coil. We know that when a current passes through a wire, it produces a magnetic field. Okay, so we get a magnetic field produced around this primary coil. Because it's an alternating current, the magnetic field is also going to be alternating. North-south, south-north, north-south, south-north. Okay, so we get an alternating magnetic field around the first coil. Now, that will cause the iron core to become magnetized in exactly the same way. When we put a magnetic material in a magnetic field, it basically extends that magnetic field. It becomes magnetized. So that means this iron core now has a magnetic field in it, which is constantly reversing direction. That means that through the secondary coil, there is a magnetic field which is constantly swapping direction. Okay, so that means we have a moving magnetic field through a piece of wire. Remember, when wire moves relative to a magnetic field, like here, it produces a current. So we're producing a current, sorry, I should say we are inducing a current in the secondary coil by simply passing an alternating current through the primary coil. Now, because the magnetic field through the secondary coil is reversing directions, north-south, south-north, north-south, south-north, it's not only reversing directions, but the way it's moving is constantly swapping. It's going that way, then it's going that way, then it's going that way, then it's going that way. So that means the induced current in the secondary coil will also be an alternating current. So by just inputting an alternating current into the primary coil, we get an alternating current induced in the secondary coil, and we get an output potential, we get an output voltage. Okay, but how does that change the potential difference? Okay, well, it turns out that the ratio of the input potential difference and the output potential difference, so the input divided by the output, is exactly the same as the ratio of the number of turns in each coil. So the potential difference in divided by the potential difference out equals the number of coils in the primary divided by the number of coils in the secondary. So what that basically means is if I have twice as many turns on the primary coil as I do on the secondary coil, then the output potential is going to be half as big as the input potential. If I had 10 times the number of turns on the secondary coil, then that means the output potential is going to be 10 times the size of the input potential. So that's how we can use transformers to change the potential difference. We don't add or take away any energy from the system, so we are keeping the same power. So we're increasing the potential difference, decreasing the current. And there you go. That's how transformers work to safely transmit or efficiently transfer energy around the country via the national grid.